Hi and welcome back. In this section, we'll take a look at implementing our very own Vision Transformer here using PyTorch. So let's get started. So open Notebook 60 and we'll begin the lesson. So firstly, credit goes to Hiroto Honda for creating this notebook here. It comes from the paper in Images with 16 by 16 words. And also here's another implementation of it here, as well as this. We use Tim, which is a Python library that allows us to load PyTorch models, pre-trained PyTorch models. It's quite useful. So I would encourage you, if you want to get more hands-on experience with using these state-of-the-art models and easily loading them into your own projects, you can take a look at this tutorial here. It's quite good. So let's begin. So firstly, you've got to install Tim, which I did. It takes about 3 seconds, and then just load the libraries, takes about 6 seconds. Next, we need to load the model. So the model we're going to load is the VIT-based PAT16-224. This was trained on ImageNet, and its resolution image size is 224. So let's begin. So let's load this model, and we use create model from Tim to create the model right here. And you can see device equal CUDA means that we're using the GPU. You can just always make sure you're using the GPU here. It should be set to GPU by default on this notebook. This takes a little while because it has to download the model in the background, so let's just be patient. Okay, there we go. It's actually not that long, 21 seconds. So now we just define some of the parameters that we're using, some transforms as well. Next, we're going to load the ImageNet labels as well as the test image that we'll be using for this demonstration. So what we're going to do, we're going to run an inference on this image from Santorini, the Greek island. So let's take a look, and it says dome. Okay, so you can see this is quite simple. We got the image here, we converted the image to a PIL, we loaded the image using PIL, and then we just put it into a tensor here using the transforms. Then we use unsqueeze and then send it to the GPU. And that's pretty much it. We just get the output out of it there. And then we get the argmax of that output using torch.argmax, which is analogous to the NP numpy argmax function. Convert it back to an int, so we can use it as an index in the ImageNet labels list that we created here, or sorry, dictionary that we created there. And then we just show the result here. So inference result is a dome. And you can use this on any image you want. So now let's dive deeper into the Vision Transform. So you would have seen this in the previous section where we take an image like this, split it up into patches. We're using 14 by 14 patches here. And 14 by 14 is 196, which is where we have N1 to N196 here. Then so this is the patch embedding. Each patch is encoded into a 1 by 768 vector here, and we use convolution layers to create this embedding. So there are some conv layers involved here, and then we combine it with the position embeddings here, and then we have a class token as well, so it's one more added to these, so it's 197 in total. And you can see n equal 197, that this is the depth. Each vector is 768, so this is a 197 by 768 matrix that we pass to the transformer encoder, and it outputs the encodings here, which is the same dimensions anyway. And then we pass it to the MLP head, which does the final prediction. That's pretty much a transformer in a nutshell. So let's take a look at how we actually split these into patches. You can just remember this is how it's done here, and this is where we get the embeddings from. You can just print this out there. You can see the image tensor size was 224 by 224 depth 3, and the patch embeddings here for the image is 196 by 768, as we saw in the diagram above. Now we can visualize what the patches actually look like for that image. Even though we saw it above, let's just generate this nice patch image here using matplotlib, and you can see this. Each of these are split up into these little cells. And that's what we use for the inputs into the Vision Transformer encoder. Next, we need to add the positional embeddings, which are trainable, or learnable, I should say. So to do that, let's just take a look at the position embed vector here. And now we can see, let's visualize some of the position embedding similarities, so you can take a look and see what that looks like. I'm not entirely sure how to interpret this chart here. They all look very similar to me, but it's probably I'm not entirely sure. Maybe I should look into it before explaining it wrongly to you guys, so I'll make a note of that and come back to this. So next we need to make a transformer input here. So this is what creates that class token here. So that's what we add to the 0th vector. So we add it to 197, so it's 1 plus 14 by 14. So let's do that, and then we just added it there. So that's quite simple. So now this is a closer look inside of the transformer, a deeper look inside of the transformer encoder itself. So you can see what's happening here. You can see the vector is input here, and then we have different processes going on. You can see it's split up now into finer detailed vectors here, or matrices. And then we just go to the parallel attention heads. This is an important block here, and it outputs it here. And then we have the fully connected layers here, which have formed the MLP head, which predicts the final class here. So let's take a look at the series of transformers. So we're using 12 different transformers in series here. So we can print this out here. You can see transformer 0 to 11, that's 12. Now we're going to see what the attention part that the transformer creates, what it looks like, and visualize it. So let's take a look firstly at the multi-attention head block, which is this here. And you can see the input to that encoder is as what we expected, 197 by 768. Next, we can take a look at the fully connected layer that expands to that dimension, and you can see what it looks like here. So this is 768 is now replaced by 2304. Next, we need to split QKV into multiple QKV vectors for the multi-head attention. So let's take a look at that. And now we need to create the attention matrix, and that is visualized like that. So now we can visualize the attention matrix for all of the patches, and you can see what they look like there. Okay, so now this is a multi-layer perceptron head. So this produces a vector, a vector that has the probabilities for each class, or basically just not the probabilities but the scores you can see for each class here. And you can see 5 to the 8 here. Let's run this and generate it on our own. 5 to the 8 is the class with the highest score, you can say. And then we just normalize it to get the probabilities out of it. And we know that that's the dome. This is just 5 to the 8 corresponds to the dome class here. I'm not sure what number this is, but it's probably something that looks similar to a dome. So that's it for vision transformers. This was a lesson that went in depth into the attention parts of the vision transformer and into the individual blocks at the end. Next, we'll take a look at how you can train your own vision transformer in Keras. So stay tuned for that lesson. Thank you.